When polygons are similar, they're the same shape, but they may not be the same size. And corresponding sides are sides that match up, like the shortest side of one compared to the shortest side of the other. Those are corresponding sides. They form proportions, and also corresponding angles are congruent or equal. The corresponding sides may not be congruent, and they probably aren't unless the two figures are congruent to each other, but the angles are congruent to each other. A dilation is a change in the size of a figure. It's either shrinking it or expanding it. It doesn't change the shape, it just makes the shape become larger or smaller. So we'll take a look at some examples of that. Here are two rectangles that are congruent. They're exactly the same shape and size. If I just expand one of them, I'm trying not to rotate it, but because that's a different transformation. So that was an expansion. They still are similar to each other. They're exactly the same shape, whether I shrink it or make it larger. Still the same shape. Corresponding sides would be proportional to each other. So this side matches this side. This was 4 units, and this was 2 units, and this was 8 units. You would know that this would be 4 units because the scale factor is 2. That is, multiply every side on this, every side length in this shorter one by 2, and you get the length of the corresponding side of the larger rectangle. So I can do 4 times 2, 4 units times 2 to get this length here. Dilations don't just apply to rectangles. You can take the pentagon and make it larger or make it smaller. Try not to rotate it because that's a different kind of transformation, but it just slips out of my fingers here sometimes. So there's much larger, and there's a smaller one. So they still have corresponding sides. Let's take a look at a triangle and do some math with the triangle. Right now, these two triangles are congruent to each other because I drew one and just copied it. So I want to go ahead and enlarge one of them. And it's pretty obvious the sides that match up are the sides that match color. So, but I want to introduce a symbol to you. The little wavy line means those are corresponding sides. So I have to, because blue corresponds to blue, but blue doesn't correspond to pink, I have to use, I'm going to use one line, wavy line, to say that the pink sides are corresponding to each other. I don't want to use one wavy line on another side, so to vary the number of little wavy lines I put in there. I didn't really need those because, you know, pink corresponds to pink, white corresponds to white, and blue corresponds to blue. So if I say, let's say this is 3 units, and I'll use a scale factor of 3 on this one. That would make this 9 units. And then I'll go ahead and put some other lengths in here too. And we'll say 2.5 for this one. So what I can do, to get back to one of the ideas in the introductory slide, that corresponding sides of similar shapes form proportions. If I match up the 2 long sides, which would be the pink sides, I could say that 3 is to 9, because these are the proportion of the corresponding sides, or the ratio of the corresponding sides. This is the proportion. If I don't know what this side is, call it n, and I could say, now I have to be careful where I put the n and where I put the length of the corresponding side, which is going to be the 2.5. If I put the length of the smaller polygon in the numerator, I have to continually do that, I have to be consistent, and put 2.5 here and n here. Then I use cross products to solve this, and I could say that 3 times n would equal 9 times 2.5. 2.5 decimal point there. Then I'm going to divide both sides by 3. That'll cancel. I'm going to go ahead and do 9 divided by 3. Then my arithmetic is 3 times 2.5 and would equal, I believe that's, I know it is 7.5. 3 times 25 is 75, so 3 times 2.5 would be 7.5. So that's how I can use ratios and proportions to find lengths that are not known of similar triangles. But I have to have a ratio. I have to be able to know at least 2 lengths from one of the triangles and match up the other sides. I'm going to make an application of dilations using the coordinate plane. So we have a triangle ABC with coordinates 2, 2, 2, 6, and 5, 4. Just a reminder that the first coordinate is how far over you go, and the second coordinate is up. K is a universal symbol for a scale factor, so in this case I'm going to double the value of each coordinate. So I'm going to say something that matches point A, which is called A prime. So this little symbol is red prime. It's not the same as A, but it kind of is the same. In fact, in this case, you'll see how it works out. So I did double the values of A to get the value for A prime, which would be 4, 4, because 2 times 2 is 4. B prime would be the point 4, 12, and C prime would be 10, 8. So when I graph these points, I go over 4, up 4. Should be located here. Then I go over 4, up 12. So I'm going to have to move this just a little bit. So over 4, up 12 would put me here. And then over 10, up 8. So over 10, up 8 would put me right there. And so I get a triangle that it's similar to the initial triangle, but it's both slid over, so it's a slide, and it's an expansion as well. And I'm sorry, that was not right. B prime should be right here, and this should be C prime.